Hello. All right, so here we had the chapter we're starting is chapter 15, by the way, and I do want to recommend that you try to read this chapter. They have some great sample problems in there, and I could see doing that this chapter. It is true that if I think it's important, I probably am going to talk about it in class, but I think somebody might want to think about reading the chapter. All right, what I was trying to motivate you yesterday about how much chemistry is actually done in a solution, and it's huge. Almost every test that they do, if they run a test on somebody, they're trying to find that things are in solution. So a lot of the equipment that chemists used have to do with finding things in a solution. We had my advanced chemistry class, they have a thing called a spectrophotometer. A spectrophotometer is a machine where, remember yesterday I was kind of making a joke and I said, I have some blood and I put it next to my ear and I say, how much iron is in you? And the solution never tells me anything. Or well, we have a machine that will tell me. And so what you can do is you can, I need kind of your attention here, just so I'm going to tell you, otherwise I'm wasting my story here. We could take a solution like this, and I could tell you how much is dissolved in there with this machine. And you say, well, how do we do that? How would you do that? Well, first of all, I would have to make what they call our knowns. I would make up solutions where I know how much food coloring was in there, and how do I know it? Because I made it. I made it that way. So what you would do is you make a thing called a standard curve. And in this case, the curve is a straight line. And what you would have is concentration versus, let's say, absorption. Okay, now, so what happened is I would make a solution that I knew was a certain concentration. Let's say a concentration of 1, and a concentration of 2, 3, 4, 5. And then what I would do is I would put that in the machine, and the machine would say, hey, how much light did you absorb? Well, did you know that blue light, it loves to absorb red? And that's another thing the machine would tell me. The machine would tell me, hey, blue stuff, what do you like to do with green light? What do you like to do with yellow light? What do you like to do with blue light? Do you like to absorb it or not? And I can actually make a graph telling me what kinds of light this thing absorbs and what kind it doesn't. So I find a nice color I know it absorbs, like red. And by the way, do you know that blue doesn't like to absorb blue? What's it do with blue light? It reflects it. It doesn't like to absorb it at all. What about green plants? Oh, they love green light, you think? No. You can kill a plant in green light. If you only give it green light, it's going to die. Why is that? It reflects it. It doesn't know how to absorb it. And so when I look at something like red on your sweatshirt, that thing's red not because it absorbs red. It's red because it doesn't absorb red. It reflects red. Okay, well, I won't get into that lesson. But anyway, you have this machine, and I know the concentrations because I made them. And so what happens is you have a nice little graph here, and then I find an unknown, like this one. Let's say you give me something unknown. You said, find out how much is in that. Okay, I will. I put my unknown in the machine, and it tells me how much it absorbs. This number right here. And then I read down. I say, yeah. It's a little bit more than 2.5. You gave me something that's about 2.7 units of concentration, didn't you? Yeah, how'd you know? And so that's really a huge thing in the science world. A huge thing in the science world. We can actually find unknowns by comparing them to knowns. So I made some knowns, and then I found an unknown. And so when I turned my blood in to the doctor and they sent it to some laboratory, they have already done knowns. They know what 1 part per million of iron is, or 2 or 3 or 4. They already know what that is. They put mine in there, And they said, you gave the same results as the 5.5 parts per million of iron. That's what you must have in your blood. And a lot of this is done with light. And a lot of it is done in solutions. I just want to tell you that a huge amount of chemistry is done with solutions. So don't underestimate this chapter. If you're thinking about being a science major or chemistry major, biology, this is actually an important chapter. Okay, so let's go with what we found out. We know, do everybody know the words solute versus solute? Everybody know solute, solvent, solution? Does everybody know the difference between those three words? Are you okay with that? All right, so let's say you know that difference. Solute is the stuff that gets dissolved, all right? And solvent is what? The stuff that does the dissolving. And what do you call it when you mix a solute with the solvent? It's called a solution. And we know the solution is not a compound, it's a what? That's from first semester. It's not a pure substance because you can make it many ways. That's called a mixture. So, anyway, there's no chemistry that went on. When I put that food color in here, there's no chemistry. It was just a physical change, wasn't it? All right, so let's go on. Now, somebody, a long time ago, I told you one of the bad news about solutions is that how many ways can you describe the concentration of a solution? That's the bad news. There are a whole bunch of them. You got that? The good news for you, I'm going to talk about one of them with this chart. It's the only time I see him use this unit, but almost the entire time, the rest of the chapter, you're going to hear me hit this guy right here. So we'll spend a little time with this guy, and we'll spend a lot of time with this guy. All right. So one way that you could describe the concentration of a solution is grams of solute per what? 100 grams of solvent. Now, I didn't do this, but this is called a classic graph in chemistry. And, excuse me. All right, so let's look at the graph again. What's on the x-axis? What's on the x-axis? You say temperature. Okay. So the water is either really cold water or it's like boiling water. Everybody okay on that? Do you understand the x-axis? What is this axis? Grams of what? Solute, but per what? Per 100 grams of water. So when they were doing the experiment, they probably had a whole bunch of beakers with 100 grams of water in it. And they said, hey, let's have some cold water. And how much of this chemical can I dissolve in there? And, oh, that's it. Okay, write that number down. And then it got warmer, and they said, hey, you can put some more in there, right? And almost every chemical, isn't it more soluble when it gets warmer? What's the only chemical on here that's not more soluble when it got warmer? Say it again.
NH3.
Yes, that's called ammonia. Yes, very good. Now, we have three words, but I want you to know, two of them are used a lot, and one of them is kind of a special word. If I take some random temperature, I'm going to take 10, okay? I'm going to do the same thing I did yesterday. At 10 degrees Celsius, kind of cold water, and I'm going to take a chemical like sodium nitrate, okay? I'm just going to pick a chemical. And here's his graph right here. Here's his graph. All right. At 10 degrees, let's go up here till we hit that graph. And then go across here, and what the world does that mean? What does it mean, 80 grams of solute per 100 grams? What does it mean? Yes?
Like 80 grams of sodium nitrate dissolved in 100 grams.
At 10 degrees, and that's it. That's all you can put in there. You cannot put more than 80. You have filled it up. What's that special word that means it's full? How would you describe this solution? You can't put any more in there. It's maxed out. What's a great word for using this solution?
Concentrated.
It's more concentrated than if I put less in there. Concentrated is kind of funny. Like, I don't know where it starts being concentrated, but Kieran, you know, what's that word? It means I'm all full. How would you describe a solution of NaNO3 at 10 degrees Celsius, and you put 80 grams of that chemical in 100 grams of water? What is it? Yes, saturated, full. I'm full. What if I only put 79 grams in there? Am I full? I must be unsaturated. Or if I put 59, you're unsaturated. There are many ways to be unsaturated solution in it. There's only one way to be saturated. Now, if under very, very special conditions, and don't assume supersaturation, assume that it's not going to happen. What if I try to put 85 grams in there? I should find 5 grams of that chemical sitting on the bottom. I can't dissolve you, no matter how much I stir you. That's it, 80. But if I were to go up to 20 degrees Celsius, then what would happen? If I went up to 20 degrees Celsius, did I go 30 yesterday? Did I go to 30 yesterday? Okay, let's go 30 again. If I go to 30, I noticed that I should have put 94 grams of that in there before I get a saturated solution. See that? Now the saturation mark's different now, isn't it? Now it's 94 grams. And anything less than 94 would be unsaturated. So now, what if, though, I made a saturated solution at this temperature, 30, and let it cool off to 10? What would happen in that beaker? I had 94 grams of this chemical in there in 100 grams of water, and I let it cool off. All right. Somebody in this row. I called on Kieran. I called on you. Somebody in this row. You had an answer. How about Julia? What's going to happen if I let this saturated solution at 30 cool down to 10? Say it a little bit louder. It's only going to hold 80, isn't it? But you had 94 in there. So what's going to be at the bottom of the beaker? 14 grams. There'll be 14 grams of that chemical sitting on the bottom, right? Now, I do want to tell you that do not assume that you have a supersaturated solution. I'm going to say almost every question I ever ask you, you do not assume that it's supersaturated, because that's a very special case. You have to do it specially. You have to watch what you're doing. It's not as easy as you think. But if I were to do this with really, really clean glassware, and I let it cool in a really quiet place, and it wasn't vibrating or anything like that, what if it got down to 10 and I didn't see anything in the bottom? What if that means all 94 grams were in there? It said, you can't do that. You're only supposed to hold 80. Well, too bad. I have 94 in there. That would be called super saturated. Now, I do want to show you, I'm going to try to run up a video here real fast, but I want to show you a couple of videos about supersat. Yes?
Yeah, so wait, that's when like it all dissolves even though it's more.
It does dissolve, and it's not supposed to.
Okay.
And again, don't assume a supersaturated solution unless I tell you, okay? Unless you have evidence of it. Yes?
So if you put like 85 grams of like sodium nitrate and like 10 degrees, would that be like 5 grams like at the bottom?
Yeah, if I had 85, yes, there'd be 5 grams at the bottom. All right. So what I want you to do, it's going to take me about 2 minutes to look at my video. And what I'd like you to do is to work on the homework on here, and then do a couple problems, and then tell me, hey, I had some problem. I couldn't do this one. So I'll be back with you in just a minute, okay? I'm gonna watch. I should have looked this up, and I'm not quite there yet. All right. This is 2 minutes. 2 minutes and 55. Okay. I like that one. I like that one too. I've seen that one. Okay. Stop. All right. Let me tell you real quick. To get ready to see here on this video. when I said that something was super saturated, it means that you're not supposed to be able to do that. But somehow the glassware is really clean. There were no scratches on the inside. These crystals are waiting to come out of solution. They should come out, but they need something to get them started. Now, I've seen people that actually just tap the side of the beaker like this, and then it would start to, all the ones that are supposed to come out would. Another way to do it is take a crystal, a single crystal of that type, and throw it in there. And all the ones that weren't supposed to be in solution, they're going to grab around there, blah, 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 and it looks like crystals are growing right in front of your eyes. So again, supersaturation, don't assume supersaturation unless I tell you, but it is kind of neat to watch. So I'm going to show you about 2 or 3 videos here, and here's the first one.
Closer. Hold on. You can't even see it. Okay, go. Okay, well, there's a crystal on. You might crystallize your. It's not gonna crystallize on your phone.
Ready?
Yes.
So realize this has been sitting there all year long like this.
What is it?
I'm
What
gonna
is
change
it?
Huh? Well,
He probably had a lid on it because even dust sometimes can do
a
it.
huge amount of these crystals dissolved in it.
Um,
It has so much of it that is called supersaturated now. Actually, it's holding more salt than water actually can.
How does that work?
Because I boiled it.
you dropped it in there?
What?
Oh snap! Oh my gosh, that's so cool! It looks like pretty. It looks like a puffball. My favorite ribbon. Oh my god.
That's so cool.
That's pretty
What
neat,
happened to
isn't
the
it?
bug? What happens if it's still over there? Ow! Cool. That was just
Now,
one
there is
drop.
one chemical that is so good at supersaturation, that's why he's getting so much.
That was Jeremy. He got it.
Yeah, I get there first.
So sodium acetate is one of the most soluble compounds, and people used to use that.
It does look kind of weird. This is so cool. Is this real? They look like feathers. Can we touch it? Are we gonna
Wait
blow
till,
it?
wait till it's all
You
crystallized.
would touch it either way. I touch radioactive things. Oh my gosh, poor Austin. You can't see like that. He does not. He's having more fun. Are you gonna break it off and give the pieces to all of us? Could we blow it? Have you touched it?
All right, I'm going to show you another one.
Well, first touch the sides.
Is it cold?
I should have had you touch
Oh, by the way,
sides.
I should have told you, a lot of heat is going to be given off when it, for crystal forms.
It's not cold, it's warm.
Yeah.
It's warmed up, so the crystallization.
Now, here's one I've seen.
Actually
Do you
releases.
remember
Just gross stuff.
what happened to Lot's wife in the Bible? What happened to Lot's wife in the Bible? Okay, now, I've seen teachers use this as a lesson to show what happened to Lot's wife.
Welcome to Chemistry Lab. My name is Jeremy Krug, and today our experiment is going to involve solution chemistry. We're going to be making a solution out of sodium acetate, which is this white crystal here, and water, which is our, of course, our clear
Okay, I'm gonna zoom it up because
Let's see what happens.
he's gonna do the same thing the other guy did.
A little tiny seed crystal of sodium acetate, and let's see what happens.
Okay, here's the second part you're gonna see is where he pours the supersaturated onto a crystal, and here's the Lot's
Acetate.
wife thing.
And pour it onto the watch glass.
Don't look back, don't
Has
look
a little
back.
seed crystal on it. Let's see
Watch.
what happens.
Don't look back. So you can kind of like make a pillar of salt. This is sodium acetate salt, but okay. And maybe I'll do one more. Let's see. Saw that one. Here's one very similar.
Just really quick, I'm gonna add one tiny seed crystal. I'm not sure if you can see on the tip of that scoop over there. All right, the tip, I'm gonna add that to my supersaturated solution of sodium acetate. And we will see it go from
Again, sodium acetate is so soluble. That's why they always use it.
In just a few seconds. Isn't that cool? So we see that the sodium and acetate ions recognize the crystalline structure of that seed crystal.
But if you think about it, if you were to think about what's happening there at the molecular level, at the atomic level, those crystals are being added like how many millions per second? Like that. And they build in these neat little crystals like that. Okay. Yeah. Okay. I may not give you 2 minutes like I thought, but I do want to show you one more thing about this chart that is probably the most difficult part is what does it mean grams of solute per 100 grams? What if I ask you this question? How many grams of sodium nitrate, how many grams of sodium nitrate do you need to make a saturated solution of 350 milliliters of water? And you look on there and say, wait, how do I look on the graph and get that? How can I get that off of the graph? It doesn't ever go to 350 milliliters of water.
Well, we also need a temperature.
Oh yeah, thank you. Let's pick one. How about 30 degrees? 30 degrees? 20 degrees?
Could you put it in full screen?
Oh, sorry. Sorry. Wait. All right. Pick any temperature you want. We'll do it. 10? Okay, at 10 degrees Celsius. All right, so what you look at is 10 degrees Celsius, and you said, hey, 80 grams of sodium nitrate will dissolve in what? Dissolve in what? 100 grams of water, and that ratio has to be the same. So if 100 grams of water will dissolve 80, I'll bet 350 grams will do more than 80, don't you think? So you set up this thing that the math teachers taught you. It's called a proportion. Ready? If 80 dissolves in 100, then how many would dissolve in what? 350 milliliters of grams of water. Same thing, grams. Can you do that real quickly? See if that works out for you. Everybody know about cross multiplication? So you go 100x equals 80 times 350. And you divide both sides by 100, and you get x equals, and I don't know, I just made this up, so I have no. Todd, do you have the answer yet? Are you that fast? What do you have? Wow, you're doing this in your head? Wow, let's see if you get it right. 280 grams, he thinks. Let me look at this in your head. Wow. What's everybody else getting? Will, what'd you get?
280.
What? Really?
280.
He did in his head. You did it in your head?
Yeah, you can multiply. Easy.
Yeah. Okay. So what you did is you multiplied by 3.5. Okay, so that's 3 times that would be 240, and half is 40 more. That'd be 280. Or you put your calculator. All right, everybody get that? Well, anyway, that's pretty much, people usually do very well in this. Once you understand this graph, they use it pretty well. And so I expect you, the homework, when you turn on Monday, you'll probably get them all right. And then on the little quiz I have for it, you'll probably get almost all those right. Get that? So I'm not worried that much about this part of the chapter. So I'm ready to move on to something else today. Okay, so you got to see that. And remember, do not expect supersaturation. It's a very special situation, so don't expect it to be supersaturated, like I tell you. All right, real quickly, let's go over here. And just want to remind you that a solution, in the first semester we said, a mixture, could you have a solid dissolved in a water, for example, in a liquid? Yeah, we do that all the time. Could you have a liquid dissolved in a liquid? That could be a solution too. Like when I buy rubbing alcohol at the CVS or Food Line, wherever, it'll say 80% rubbing alcohol. What's the other 20%? Water. So you can have a mixture of liquid and liquid, can't you? When I buy some kind of soft drink, I know there's sugar dissolved in there. I know there's artificial coloring dissolved in there, some artificial flavoring dissolved in there. There's something else in there, a gas. There's a gas that's dissolved in there. What's that? Carbon dioxide. That's why it's called carbonated drinks. And so here, it says here, you can have a gas. What is air? What is air?
A mixture of gases.
It is a mixture, isn't it? So you could have a solution of gases, couldn't you? A gas and a gas solution. Now remember, solutions cannot be pure substances because there's many ways to make them, right? There's only one way to make NaCl. All right, and that's what this little chart's all about. It just talks about all the different combinations you can have. Now, what I want to do is, if you look over here again, we've pretty much talked about this right here, and that had to do with the solubility graph, didn't it? About the only time I'll ever even ask you about these kind of units would be on the solubility graph. As a matter of fact, that's about the only time I see it in a chemistry book. And somebody thought, well, that's the way the experiment was done 100 years ago, and it's still good, and I'm not going to change it. Okay, but now what I'm going to do is show you about another way to make solutions. Now, what I have, and I think it's on this page here, and it's kind of handwritten, so... And this is a very small part of the chapter, so I'm not going to spend huge amounts of time on it. Did you know that another way that you could make a solution besides grams per 100 grams of water, we could do this. We could do percent by mass. And this is easy. You're going to like these, okay? These are easy. I need 800 grams of 20% by mass of NaCl. Well, the chart says that you would have to do grams of solute for 100 grams of solution. So let's take a look at this right here. I need 800 grams of a solution that's 20% by mass. Now, what if I ask you, I said, that's going to be a quiz question for you. Ready? Go make it for me. Go make this for me. You say, well, wait. I've never made this before. Okay, let's stop and think. You've never made it before, right? What do you think I should do? Just give me an idea. Take a guess. How would you make this? An idea. What do you think? It's 20% by mass. Salt. Yes.
Well, you could make, depends on how big the solution you're going to make, right?
I need 800 grams. I need 800 grams when I get done.
Okay, so then you're going to have 800 grams of sodium chloride, and then you're going to have...
Wow, that's a lot.
Wait,
If you have 800 grams of sodium chloride, then my solution can't have any water because the total has to be 800 grams.
okay. I thought you were saying that, okay, all right, yeah. So then you're going to have, it's going to be, well, I don't know, 20% water.
You can do that other one in your head. You can't do this in your head. I thought the other one was much harder than this one, huh?
No, you just multiply. Okay, it's 160 grams of sodium chloride, and then the rest is silver.
Yes. Now, I'm going to tell you that I'm not going to spend a huge amount of time on this. I want you to tell you that a lot of people do make solutions like this. It's so simple. Does it involve anything that has to do with moles? No. So when I was a biology major, almost every time I saw a biology lab, it seemed like all the solutions were made by mass, percent by mass. Now, I'm not trying to say that biology teachers didn't like to do chemistry. I'm just saying that it seemed like all the biology people made their solutions like this. And didn't have to worry about moles. And he did this. So what's 20% of 800 grams? 160 grams. So I need 160 grams of NaCl. And how much water am I going to have then? What's the rest? How much water then? I'll help you. Let me help you.
So 640.
How much?
640.
Yes. don't drink it, but, okay. But anyway, so if you want to make this is simple. You simply say, you want 20% of that 800 grams to be salt. Okay, I'm going to do that. What's 20% of 800 grams? 160 grams. Well, then the rest has to be water. So I add this much water to this much salt. I stir it up. I'm done. Pretty easy? Yes.
What's that word thing? What is that next to it?
Enjoy. Stir and enjoy. I'm just kidding. You don't really drink it. But, all right, ready? Pretty simple? What do you think? Pretty simple? Now, let's do another one. I need 600 milliliters of 8% alcohol by volume. Percent by mass? No. Percent by volume. Same idea. Watch what happens. You do it. I've never done that before. All right, think about it. What if you had to make it? I need 600 milliliters of an 8% by volume solution. And again, I'm not going to spend a huge amount of time because this is a minor part of making solutions. I'm going to get to the big guy here. The big guy's coming right there. Who wants to help me? Olivia, you do it. Olivia, tell me out. I have 600 milliliters of solution. 8% of it by volume has to be alcohol. So how much is going to be alcohol? Yes? What do you think? Gotta hurry up a little bit. What do you think? Olivia's gonna do it. What you got, Olivia? Good. It's 48 what though? Not grams. Of what?
What's the formula for
Yes. Yes. And then what else you're gonna add?
Mr. Feeney, what's the formula for alcohol?
Okay, because there are many alcohols.
I guess just standardized.
So, no, it wouldn't be standard because you could do a methyl alcohol, ethyl alcohol, propyl alcohol. So I can't tell you that because it's not like, I know what you're thinking, like NaCl, it has a molar mass, but there's so many alcohols. Now see, in this case, can I tell you something?
Yeah.
I don't have to worry about molar mass because I have a bottle of this alcohol, whatever it is, and all I do is pour 48 milliliters into a graduated cylinder. And then how much water do I need? Yeah. All right, 552. All right, that's it. Now, again, I'm not here to spend a huge amount of time on this, but I want to tell you that I've seen a lot of people in the biology world, and they like to make solutions like this. Now, why? Well, it's simple. It's very, very simple to make. You even right now, without any lessons, you know how to make these, don't you? And so that's what they like. It's simple to make. And I'm sure that chemistry for a while did the same thing. But then something happened. When they came up with the mole concept, something changed. They knew that was the secret to chemistry, was the mole concept. So all these other concentration units they had, that wasn't going to fit. It was okay. But now, ready? How many moles is that? Well, I don't know. And you can't get to moles very easily. So somebody developed a new concentration unit, and that's the star of the show, without a doubt. Without a doubt, we need to know the star of the show. So here we are, the star of the solution world. Now, the abbreviation for molarity is capital M, okay? And capital M means moles of solute per liters of solution. Now, this is strange. This is very strange because so far before this, it was so many grams of solvent. It was so many grams, and this one's not. This says liters of what? Not solvent, but what? Solution. And so what we're going to do here is I need 500 milliliters of a 2.5 molar NaCl solution. So let's write down the equation. Molarity equals moles of solute per liter of, not solvent, but what? So, what we're going to do is, I'm going to show you in this entire chapter, here's what the author is, he's going to try to trick you a little bit. You're not going to get tricked. What if they give you moles of solute and they give you liters of solution? You simply put it in your calculator and you get the answer. But then they get tricky. Watch. They'll put grams of solute and liters of solution. He said, you're not going to trick me. You're going to give me grams of solute? I'm going to do what? Change them to moles. Then I'm going to divide. Oh, darn it. So I had you tricked. And then sometimes they'll give you moles of solute and milliliters of solution. You're not going to trick me. I'm going to change the milliliters to what? To liters. See? And then the trickiest one of all, they'll give you grams of solute and milliliters of solution. And they act like you'll be able to do it, won't you? If you understand, you give me moles, you give me liters of solution, I will find molarity. I will. All right, so let's try it. Do I have either one of these right now? Do I have that? No, I don't. Where's that? Where's that at? How do I do this? If I had to make this solution, oh, by the way, what's the molarity? What is the molarity? What's the molarity going to be? Now, what does capital M stand for? Moles per liter. You get that? So when I get over here, I better have moles here, and I better have liters here. So I need moles here, I need liters here. Now, do you have moles? No? I'll figure that out. Do you have liters? Sort of. What's 500 milliliters in liters? What's the shortcut for that? I can do factor label, but 500 milliliters, how much is a whole liter? How much is a whole liter? How many milliliters? I had this in the first semester. What's milli? Uh-oh, lost it. Milli's 1,000th, isn't it? It takes 1,000 milliliters to be a liter, doesn't it?
This is half of
Well, I have 500. Oh, you mean if I take the decimal and move it 3 places, that, oh, I can do this. All right, so there, I got that number. And now, all I have to do is figure out how to make this solution. So what's going to happen here is, can you guys do the math here? This is 0.5, and this is like 2.5 over 1 if you like doing a cross multiplication, but you can also just multiply both sides by 0.5, can't you? X equals 2.5 times 0.5. What's that?
1.25.
All right, now let's see how alert you are on a Friday. What units would this be? If I multiply both sides times liters, how do you replace big M? What's big M really mean? Big M is really what? Moles per liter, and you're going to multiply it times what? So what's the unit here? Okay, all I have to do is go find 1.25 moles of sodium chloride, and I'm set. So I hand you a jar of sodium chloride and said, make it for me. You say, well, just a minute. I'm certified, so I know how to do this. 1.25 moles of NaCl, and what do I need here? If I want to make this solution, don't I need to figure out how many grams to put in there? Are you with me? I want you to make this solution, right? All right, so what do you think? What do you know already?
We put 1 mole on the bottom of the other side.
Yes, 1 mole of NaCl is, what's the molar mass? So we've got 23 plus 35.5. 23 plus 35.5, what is it?
58.
0.5, right? Chlorine is 35.5. Now, go ahead and give that to me. And we're about done. We're about ready to make this solution. I can't do that in my head. I know I can't. Ooh. Look, Maddie Raymond's got it. Madeline, you got it? Maddie, you got it?
Oh, yeah. 73.1 grams of NaCl.
Is that what everybody else is getting? Is that what everybody's getting? Now, I want to show you something. This will be the last thing I do today. Now, these other concentration units were nice, and they were simple, but they didn't get into the mole world. You see that? And so molarity was created with intent of getting quickly into the mole world. Now, let me tell you the price that the chemists had to pay. I'll go back and get something for you. Now, even though I had you learn what the name of this was, you really didn't know why I need these. And so I want to show you. I'll go front here. This is called a volumetric flask, and it didn't exist before the word molarity. And because before, I put this much in there and this much water, you mix them up, and you're okay. But this guy, how do I make this solution, all right? And I need about 5 more minutes, okay? I know, number one, I'm gonna go weigh out 73.1 grams of sodium chloride. Now, what am I gonna do with it? I'm gonna put it in here, okay? Now, by the way, I can buy these with different volumes. Now, this one is the wrong one. What's my total? Oh, no, this is the right one. Good, I picked up the right one. I need 500 milliliters of solution. This is called a 500 milliliter volumetric flask. Everybody see that? Now, I know you're not going to like this, but before the word molarity came out, they didn't need these special flasks, and these are kind of expensive. So I would put that 73.1 grams in here, and then I start adding a little water. I'd stir. I even have a stir station. I can do that. And then I add some more water. I add some more water. I add some more water. How much water do I add? I don't know. I don't really know. Because I know I don't add exactly 500 milliliters because some of the space is taken up by the salt, isn't it? I don't even have to know how much water. All I have to know is what? What is the total volume of solution? The solution has to be 500 milliliters. So you put this in there and add distilled water, and stir, and go up here till the bottom of the meniscus is right there, and you're done. And what do I hold in my hand? I hold a solution. I hold 500 milliliters of solution. Oh yeah, what's the concentration? 2.5 molar. What does that mean? There's 2.5 moles for every liter. I only have half a liter, don't I? So I have half a mole. So what I'm trying to say is, nobody even owned these before the word molarity came up. And so imagine this. Every lab in the world had to go buy some special volumetric flask. And why? How, who would do that? Why is this so important? Why is this so important to have molarity? I don't even like that concentration unit. I like the other ones that were easy. And I'll tell you why. Because you're going to find out in this chapter that if I take this this equation right here, okay, and I rearrange it, you get this. Molarity times volume in liters equals moles of solute. Now, do you remember stoichiometry? You had, here's a chemical and another chemical, and it yields another chemical. Remember that? See that? And here's how you do stoichiometry, right? What if I tell you I'm going to give you 2 liters of 4 molar NaCl. Now, why is this so important? Okay, look what happens. If I give you 2 liters of 4 molar NaCl, I'm going to give you a solution, right? How can I get into stoichiometry? And watch what happens here. What's molarity times volume? Moles. Now what is that number? What is 2 liters? What is that? What is that? What's molarity times volume here? I'm in the mole world. Molarity was so important and it's so quick that you could get into the mole world that every chemistry lab had to have special flask made for them to make a molar solution. And it was worth it because see how quickly I can take molarity times volume and get into the mole world. Once I get in the mole world, you can't stop me. Okay, now I know you're only 10th graders, and maybe you didn't understand how important that was. Maybe I'll try to get to you on Monday, teach you again how important that is. But molarity will be the star of the show. It is the star of the show.